In this video, we're given a series of oxidation-reduction half reactions, and we got to calculate the Gibbs free energy, delta G. Notice that naught. That naught means we're in standard state. And then we have to calculate the equilibrium constant. The equilibrium constant C, the C stands for concentrations. Remember, no solids in the equilibrium constant. So first thing first here, in these types of things, equations, you got to remember that they're all interrelated. The thermodynamic quantity Gibbs free energy is related to E cell, which is the cathode minus the anode, where we add the cathode and anode reactions together. It's also related to equilibrium constant K. So somewhere or the other, we got to use a combination of these equations that relate thermodynamics, Gibbs free energy, equilibrium constant, and the E cell. Okay, notice all of these are at standard state by the symbol of the superscript naught. This is called the naught superscript. So let's break down this reaction into its oxidation and reduction half reactions. Right. So the first half reaction we have here is a magnesium solid going to Mg plus 2. Let's go ahead and balance that with 2 electrons. And what is this in terms of its voltage? A reduction potential table is shown here. And magnesium plus 2E minus is minus 2.37 volts. Here we gain 2 electrons. But in the problem, we lost 2 electrons, so this is going to be a positive 2.37 volts. And then finally, we have lead plus 2 going to lead solid, and we will balance out the charge with 2 electrons. Here we gain 2 electrons, so that's a reduction. And here, that's right here, lead plus 2 going to lead solid is minus 0.13 volts, so we keep it as is. And now we just add our corresponding oxidation, which is this one here, where we lost 2 electrons, and the reduction here, where we gained 2 electrons. And so this is a 2 electron transfer reaction. And our final equation is just the same as above. It's going to be magnesium solid plus lead plus 2 aqueous. Again, it's the same thing here. Magnesium plus 2 aqueous plus lead solid. What's important is our final value for the battery, 2.37 minus 0.13 volts, is positive 2.24 volts. With that being said, we can use some of our equations here in this little triangle to try to get delta G as well as equilibrium constant K. So let's see, we can get delta G here. Okay, let's get delta G here from this equation, because we already calculated E cell, right, which is 2.24 volts. So delta G at standard state is equal to minus NF E cell. And this is a 2 electron transfer reaction, so minus 2. F is a constant that I'll give you. It's 96,500 coulombs per mole. I just want to tell you that 1 coulomb is equal to 1 joule over 1 volt. Okay, so coulombs over mole is actually 1 joule over volt mole. Okay, this is just a derived unit. So joule over volt mole. So the 2 moles of electrons cancels out with the 2 moles of electrons here. And E cell is 2.24 volts. So the volt here cancels out with the volt there. So doing this on my calculator, getting a negative value, the negative value means it's exergonic. And the negative value means that the reaction is good to go, pretty much favoring the forward side. Very large number here, minus 4.32 times 10 to the 5th joules over mole. This is what I get on my calculator. You can simplify it as minus 43.2 kilojoules per mole, okay, dividing this number by 1,000. All right, so we got our value of delta G. This is going to be an exergonic reaction. So the final step in this problem is to figure out K. So let's go ahead and utilize this equation to solve for K. We already just figured out delta G naught here. Okay, R is constant, T is temperature. They tell us this is at 25 degrees, hopefully. Do they tell us it's at 25 degrees? Yes, they tell us it's at 25 degrees. So we can go ahead and utilize this equation, solving for natural log of K and then taking the inverse natural log to get K. So let's go ahead and do that. And we already figured out the value for delta G naught. The value of delta G naught is minus 4.32 times 10 to the 5th joules over mole. And by the way, K is unitless, so should not have any units. Minus RT, R is minus 8.314 joules over mole Kelvin. So I'll give you that constant on any exam. And T is 298 Kelvin, which corresponds to 25 degrees C. So you can see here the joules over mole cancels with this joule over mole. That Kelvin cancels out with that Kelvin. All of this should equal to natural log of K. So K should be e to the power of whatever this number is. So let's go ahead and do that on our calculator. So here we have minus 4.32 times 10 to the 5th divided by parentheses 8. Actually it's minus 8.314. Times 298. Okay, don't forget the minus signs cancel out with one another. And so that's equal to natural log of K. To get K, we will take the inverse natural log of that and get a very large number of 5.31 times 10 to the minus 75, 10 to the 75th power. That is the equilibrium constant for this reaction. Okay, couple that, this huge number, with the positive voltage of 2.24 volts, the minus sign of delta G showcasing that it's exergonic, all tell us one thing, that this reaction dominantly is pointing towards the right. All right, let's look at part B here. Once again, calculating delta G naught and Kc equilibrium constant for this oxidation reduction reaction. So we're going to split this apart into its corresponding oxidation reaction and split it apart into its corresponding reduction reaction. So let's go ahead and do that and get our voltages from the standard reduction table. So first thing I see here is Br2 liquid going to 2Br minus. So Br2 liquid going to 2Br minus. Let's balance the minus 2 on the product side and put a minus 2 on the reactant side. So here's a reduction reaction, Br2 liquid gaining 2 electrons to become 2Br minus. And let's see where that goes here. You see that right here. Br2 liquid plus 2 electrons goes to 2Br minus, positive 1.07 volts. Next one obviously has to lose electrons because this half reaction gained electrons. So it's going to be 2I minus going to I2. Let's go ahead and balance the electrons here. Minus 2 on this side, minus 2 on that side. So I minus going to I2 solid. And where's this here on our table? Right here. Okay, I2 plus 2E minus goes to 2I minus. It's the flip of this, so we're going to have to flip the sign. Flipping the sign gives us minus 0.53 volts. The electrons cancel out. 2 electrons here on the reactant side cancel out with the 2 electrons on the product side. Let's go ahead and rewrite it, realizing it's just the same thing as the original problem. What we have is Br2 liquid plus 2I minus aqueous is going to give you I2 solid plus 2Br minus. Okay, same thing here. What we're really interested in is the E cell of this battery, which is 1.07 minus 0.53, which is 0.54 volts. So this is a positive voltage for E cell at standard state. All right, let's go ahead and solve for delta G here. So our equation once again is delta G naught is equal to minus F E cell. This is a 2 electron transfer reaction. So it's going to be minus 2 moles of electrons. F is 96,500 joule over mole volts. And E cell is 0.54 volts. So the volts cancel. This mole of electrons cancel out with this mole of electrons. And this is what you will get in joules. So doing that on my calculator, getting a value of minus 104,220 joules. Again, the minus sign tells you that this is an exergonic reaction. Exergonic favoring the product side. Now we have to solve for Kc, the equilibrium constant for this reaction. So even though the reaction is dominantly favoring the right-hand side, maybe some of it, a small portion of it, favors the right-hand side. So let's go ahead and solve the equilibrium constant for this reaction. The equation for that is delta G naught is going to equal to minus RT natural log of K. So K, the C subscript, stands for concentration. The natural log of K is going to equal to delta G naught divided by minus RT. So plugging in numbers, minus 104,220 joules over mole. R, the minus R is minus 8.314 joules over mole Kelvin. Tell us T here, this is at 298 Kelvin. So all of that equals to the natural log of K. So let's solve for this and then take the inverse natural log to get K. We'll do this in one fell swoop on our calculator. So the minus sign and minus signs actually cancel out with one another to give us plus. So minus 104,220 divided by minus 8.314 times 298. And that's division. That equals natural log of K. So to get to K, we will take the inverse natural log. The inverse natural log is E. And doing that, it's 1.86 times 10 to the 18 as the value of Kc. Again, a very large number, which corroborates well with our positive 0.54 volts, which we saw here. So 1.86 times 10 to the 18. Remember, the equilibrium constant is unitless. And in fact, all our units cancel out. Moles cancel, joules cancel, Kelvin cancel, leaving us with no units. The equilibrium constant has no units. Supplement part C, we will break this down into its corresponding oxidation half reaction, the corresponding reduction half reaction, and use our equations to solve for delta G and Kc. We first have to solve for E sub cell at standard state. So let's solve for E cell here, which is the combination of the cathode and the anode. So first thing we see here is Fe plus 2 going to Fe plus 3. I'll avoid the 4. We're sort of breaking this down. We'll get the 4 back later. This is a 1 electron transfer. This loses 1 electron. Plus 3 minus 1 is plus 2. And what is that in terms of the voltage? We see that right here. Here we gain an electron in our reduction table, but this is actually an oxidation. We lose an electron. So we have to flip this. Flipping this gives us minus 0.77 volts. Do this one here, O2 plus 4H plus is going to go to water. Actually, let's just avoid the superscripts. Excuse me, let's avoid the coefficients for now. So we have 2 oxygens here, so that's going to be 2 oxygens. 2 times 2 is 4 hydrogens. So I'm going to need 3 hydrogens here. So 3 hydrogens plus 1 hydrogen is 4 hydrogens. 4 hydrogens, 2 oxygens, 2 oxygens. And now we will balance this out with electrons, E minus. And this is going to be a 4 electron transfer reaction. Right, minus 4 plus 3 is minus 1. Minus 1 plus 1 is 0. So what is this in our reduction potential table? So our 3H plus H plus here actually is 4H plus. plus this is actually 4H plus. It's a 4-electron transfer reaction. And looking for that here. Where do we see that? We see it right here. So O2 plus 4H plus 4 electrons goes to 2H2O. This is a reduction half reaction, gaining 4 electrons. And here we are gaining 4 electrons as well. So this is positive 1.23 volts. Okay, let's rewrite this out here. So we have Fe plus 2 going to Fe plus 3 plus E minus at minus 0.77 volts. But let's multiply this bottom equation by 4 to cancel out the free electrons. So let's rewrite this top equation. This top equation is gaining 4 electrons, so the top equation is a reduction. Bottom loses, actually it's going to lose 4 electrons because I'm going to multiply it out by 4, so that is an oxidation. And now we should get the same problem that we got here. What's powerful is that now we got the E cell, the voltage here. Okay, this is positive 1.23 volts. So it's going to be 4 Fe plus 2 plus 4H plus O2 gas is going to give you 4 Fe plus 3 plus 2 H2O. Minus a 0.77 will give us the voltage, and that is 0.46 volts. Okay, so this is a positive 0.46 volts. It's a 4-electron transfer reaction. Okay, 4-electron transfer reaction. 4 electrons get transferred. 4 electrons get lost by Fe plus 2 to become Fe plus 3. Those 4 electrons are gained by hydrogen ion and oxygen to give us water. So now let's figure out the delta G and the Kc for this reaction. All right, so to get delta G free energy change, it's going to be delta G naught is equal to minus NF E cell. That this is a 4-electron transfer reaction. So N is going to be 4. So we have 4 moles of electrons. F is 96,500 coulombs over mole, but 1 coulomb is equal to 1 joule over volt. So it's actually going to equal to joules, 1 joule over volt. Joule over volt mole is the actual derived unit. And then E cell is what we just calculated before, and the E cell that we calculated here in this problem was positive 0.46 volts. A positive E cell tells us that this is a spontaneous reaction. So doing this in our calculator, of about minus, it's exergonic via the minus sign, minus 177,560 joules per mole. You can see the moles cancel. This is a moles of electron. Volt and volt cancel. So delta G naught is exergonic. The minus sign tells us that. Sometimes you can say minus 178 kilojoules per mole, but that'll be up to you. And now let's go ahead and figure out K. So delta G is also equal to minus RT natural log of K. So delta G naught divided by minus RT is equal to natural log of K. So let's plug in numbers and take the inverse natural log to get our equilibrium constant, K. So delta G naught is something we already established as minus 177,560 joules over mole. R is minus 8.314 joules over mole Kelvin. And T, just want to remind everyone that the T here for all these problems is at 25 degrees C. Let's go ahead and convert that to Kelvin, which is 298 Kelvin. Okay, all of that has to equal to natural log of K. Units, Kelvin cancel, joules cancel, moles cancel. So we'll solve for this quotient, take the inverse natural log, which is e to the power of this number on our calculator will give us K. So let's do that in one fell swoop. Also, the minus signs in the denominator cancels out with the minus sign in the numerator. We have here minus 177,560 divided by minus 8.314 times 298, close the parentheses, and getting us that value here, 71.66. That's natural log of k. To get k, we'll take the inverse natural log of that number, which is e, and getting an answer of about 1.33 times 10 to the 31th power. So that is our answer. Two things I want to tell you is that the very, very large number of k tells us this reaction is very much going in the product side. Another thing that tells us it's going into the product side is our positive 0.46 volts. Another thing that this reaction favors the product side is the negative sign of the delta G, which tells us it's an exergonic reaction.